Alright guys, I'm a simple man and I don't know much, but if I do know one thing, it's that buffers freak you guys the hell out. So here we go, I'm going to show you how they work math-wise with the Henderson-Hasselbalch equation. You can calculate the pH of a buffer if you know the pKa of the acid that made the buffer, and you know the ratio pre-equilibrium of the acid and its conjugate base in the solution. Check it. Start with 100 milliliters of 0.1 molar acetic acid, pretty standard. Acetic acid I'm going to write as HAC, and the pKa is 4.8, accepted. How does the pH change as we add strong base NaOH? I'm going to assume we're adding this as a solid because it's going to make my calculations easier. I don't want to have to account for volume changes if we're adding one thing to another. Alright, so check it out. I made you a little chart so you can understand what's going on here. This is the amount of NaOH that we're going to add, and we're going to do a calculation for every single one of these. Yeah, I don't care. This here is going to be the moles of acetate that we formed. This is the conjugate base. This is the moles of acid. Now notice we're starting with straight up 0.1 moles per liter and 0.1 liters. So we're starting with 0.01 moles of the acid. Check. And I did my own little equilibrium ice table to figure out what the pH of that solution is. It's 2.9. Here's the deal. We're going to add 0.05 grams of NaOH to this solution. If you do one of those, mass divided by molar mass kind of things, you realize that this is 0.00125 moles of NaOH. What does that mean? Well, I'm going to do a little reaction here for you. When you mix acetic acid with a strong base, NaOH, or any strong base, what you end up with is a salt, in this case sodium acetate, plus water. Oh look, that's a regular acid-base neutralization. Acid plus base makes salt plus water. Check. You're starting with 0.01 moles of acetic acid, and we're adding 0.00125 moles of NaOH. So, after the reaction, what happens? They react in a 1-to-1 ratio. This one runs out first, we're left with no NaOH remaining. We've lost 0.00125 moles of the acid because it reacted away, which leaves us with 0.00875 moles of it. See, we lost that much acid. That minus that gives us that. That means that we formed 0.00125 moles of this sodium acetate, or conjugate base. And we formed some water too, but I don't care about water because it doesn't appear in equilibrium expressions because it's a liquid. Plus, we're doing the solution in water, so it's not like that made a difference anyways. Here's what I want to point out. This is your acid. You started at 0.01. You added strong base, and you've shifted some of the acid into conjugate base. That's what adding the strong base did. So, after you add 0.05 grams of strong base, you end up with 0.00125 moles of conjugate base and 0.00875 moles of acid. Now, this is pre-equilibrium. I haven't accounted for the fact that there's like some shift here based on the Ka. But luckily for you guys, you don't have to know that. You just have to use the Henderson-Hasselbalch equation. This is why I love it so much. If I could marry it, I would. Amount of acetate, 0.00125, divided by the amount of acid, 0.00875. Take the log of it and add the pKa, which was 4.8. Once I've added 0.05 grams of NaOH, my pH is now 3.95. Let's write that down. That is a money number. Adding 0.05 grams of strong base, our pH went up a whole unit. Now, I'm only going to do this once more the long way, just to show you how it works. Then I'm going to take a little shortcut. Let's add another 0.05 NaOHs. That takes us to 0.1 total. So what we've done is we've started with 0.01 HACs, or acetic acids, but now we've added 0.0025 moles of NaOH. After the reaction, that leaves us with 0.0075 acids, none of that, and 0.0025 conjugate bases. So let's use the Henderson-Hasselbalch equation. Can you see all that at once? Yes, you can. And you can see my calculator. Base divided by acid. Take the log and add the pKa. My pH after we add that much ends up being 4.32. Wait, hold on. Wait, what? We added 0.05 grams of NaOH and the pH went up by 1. We add another 0.05 and this time the pH only goes up by 0.4. Does that make any sense? The answer is yes. That's what makes it a buffer. As you get closer to the pKa, this solution will resist changes in pH, even if you're adding the same amount of NaOH each time. Want me to prove it? I will. Check it out. We're going to do this one more time, adding another 0.05 grams of NaOH. Start with 0.01 moles of acid. Add another 0.05 grams of NaOH. Do your reaction. You're left with 0.00625 moles of acid, and you created 0.00375 moles of the base. Getting tired of this yet? I'm not. I'm pumped. All right, base 0.00375 divided by acid 0.00625. Take the log of that. Add the pKa, 4.58. Let's write that in. 4.58. Man, this time the pH only went up by like 0.26. How is this happening? I'll tell you how it's happening. The buffer is resisting changes to pH even though we're adding the same number of NaOH molecules at the same time. Alright, now what you'll notice is that as we're doing these calculations, we're adding the same amount of NaOH each time. We started off with 0.01 HACs. I notched it down by 0.00125, notched it down again by 0.00125, and again by 0.00125. So you just keep doing that, and you end up with different pHs. So what I'm going to do here is take a little shortcut. You can just follow along by doing the calculations yourself and pausing the video. After we add another 0.05 grams of NaOH, we end up with 0.05 of these and 0.005 of these. 0.005 of these. Oh, wait a second. The amount of acid and conjugate base is equal in this case. 0.005 divided by 0.005, take the log of it, and add the pKa, and you end up with a pH of 4.8. Oh, look. Once we've added just enough NaOH to convert half of the acid into conjugate base, that's when the pH is the pKa. Half and half, exactly. And then you end up doing the calculations again. What you'll notice is that as you get farther and farther away from this equivalence point, the pH starts rising faster and faster and faster until you get here. Once you've added 0.04 grams of the NaOH, you're going to have converted everything to conjugate base, and you're going to have no acid left. You're going to have to do a regular Kb equation to get the pH at this point. I honestly don't know what it is. I'm going to guess that it is 6.7, but don't quote me on that. And then as you add even more NaOH, there's no more acid to titrate, so now you're just adding raw OH minus. That makes your pH go through the roof. The point here is because of the Henderson-Hasselbalch equation, the pH is more resistant to changes the closer you are to the pKa. All right, hey guys, that's it. 10 minutes. Nice little timing. Best of luck.